Hello, good evening to everyone.
Good evening, sir.
Yes. So we will wait for some time so that the other participants can join in. So kindly bear with me. We will start the session as usual at 7:10 p.m. Yes, good evening to one and all. It is 7:10 and I think we can start the session. So, allow me to share my screen. Yes, good evening to one and all. Welcome to this live interaction session. This course is brought to you by NPTEL, and the title of the course is Advanced Reinforced Concrete Design, and the course instructor is Professor Surya Prakash from IIT Hyderabad, and presently we are having the 6th live interaction session. So we are going to continue our study on the behavior of lectural members. So in the last week we had dealt with the singly reinforced beams, and in this week we are going to be studying about the singly reinforced and the doubly reinforced cross sections. Singly reinforced when it is acted upon by some compressive load, and some analysis on the doubly reinforced cross sections. So my name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow working in the Department of Civil Engineering at IIT Delhi, and I warmly welcome all the participants, and I hope that we can have a very educative and interactive session today. So before starting the session, I would like to open the floor to if there are any questions from the audience. Kindly feel free to let me know. So if there are any questions from the participants, I request you all to let me know, or else we can start with the session. So there were a few questions on the discussion portal. So as I was mentioning, this is an opportunity for those to join the session and resolve if they are having any doubts. So I am here. I am part of the team that prepares the assignment questions, and every week I go through sir's lectures. So if there is any questions, I encourage those participants who are not able to join in this week, I request all of them to join in the coming weeks, so that we can resolve the doubts together and move forward as we go along in this course. So if there are no questions, I would like to start the live interaction session. So the protocol is going to be the same. First we are going to start with a brief summary of the this week's lecture, and I'm going to keep this week's summary very short, because it was highly mathematically involved and numerically oriented. And after that I have prepared certain questions, and we can after 5 minutes of summary we can go ahead and discuss this week's questions. Okay, so with that I'll start. I hope that my screen is visible to all of you. Can any of the participants kindly confirm if my
Yes, sir, it's visible.
yes, thank you for the confirmation. So Presently, we are in the week 6 of this course on advanced reinforced concrete design, and we are dealing with the topic of behavior and design under behavior and design of flexural members under flexural loading. So in the last week we had dealt with the analysis and design aspects of the flexural members, of singly reinforced flexural members. This week we are going to deal with the topic of effect of axial compression on moment curvature analysis. So as we discussed in the previous week, this moment curvature analysis is nothing but the development of the relation between the moment of resistance developed by the beam and the curvature it undergoes. So these are broadly the expected learning outcomes to develop the moment curvature curves for reinforced concrete sections under bending along with axial compression. So there can be effect of axial compression acting on beams. So we are going to delve into that topic in this week, and we are going to discuss the effect of axial compression on the moment curvature behavior. So whenever there is an axial compression loading acting on the beam, what would be its influence on the moment of resistance, and what would be its effect on the curvature? So we're going to discuss about those issues in the form of numericals. So essentially we are going to define this axial compression, that is P, through this relation, that is x into f prime c into ag. Ag corresponds to the gross cross-sectional area of the beam, and f prime c is the compressive strength of the concrete cylinder. And when it is less than 0.2, so we consider it as a beam action. However, when this x value, this load factor is greater than 0.2, we consider it as a beam column action. So we're going to be discussing about both these actions in today's numerical examples. So in the previous class we had referred to this simply supported beam. What happens when there is a representative uniformly distributed load, let's say W per unit length, and there is a representative point load W? What happens to the bending moment diagram? And then we analyzed what would be the compressive force that is developed and the tensile force that is developed, and based on the couple, these two forces which essentially acts as a couple, and depending on the length of the lever arm, that is the length between these two forces, we determine what is the moment of resistance. In this week we have an additional force that is acting upon the beam, that is the axial compression. So based on the principle of equilibrium, we need to balance out the forces that are acting on the beam. So we have the axial force P and the tensile force that is acting along the right direction. So that is balanced by the compressive force which is acting along the left direction. So this would be the equilibrium equation, that is tensile force in steel plus axial compression should be balanced by the compressive force in the concrete. So in order to develop the relation between moment and curvature, the analysis procedure is somewhat similar to what we did in the previous week also. So we need to choose a particular strain value within concrete in the extreme compression fiber, that is epsilon c. Then we need to assume a value of x. So x represents the depth of neutral axis. Then we need to calculate the value of compressive force and tensile force that is developed on the beam's cross section. Then we need to evaluate in terms of this force equilibrium. We need to satisfy this condition, that is compressive force in the concrete should be equal to tensile force within reinforcing bar plus the actual compression. So if it is met, then we proceed to determine the value of m and phi. Otherwise, we are going to increase or decrease the value of the depth of neutral axis. This is essentially an iterative process. And in the previous class, we saw how we can use Excel sheet in order to balance these forces and then ultimately determine the value of m and phi. So we are going to be delving into these procedure in the form of numericals very shortly, and then we solved some example problems corresponding to 0.1 f prime c into ag. So it can be defined as 10% of the actual compressive force, considering actual compressive capacity, considering only the strength of concrete. So then we proceeded to determine the moment and curvature values corresponding to different values of strain, and yes, I am going to skip this because we are going to be dealing with them in a detailed fashion in our numericals today. So after finding out the moment curvature relation corresponding to 10% of the actual capacity, we proceeded to determine the moment curvature relation for 30% of the actual capacity of the beam. Then we essentially compared what is the influence of axial compression on the moment curvature behavior. Okay, so we're going to be discussing more about them in the form of numericals. Then in the second part of this week's lecture, we dealt with the topic of effect of compressive reinforcement on the behavior of the flexural members. So what would be the effect of compressive reinforcement on the moment curvature analysis? We dealt with this topic. So yes, so we discussed what are some of the reasons for providing the compression reinforcement. So broadly, I'd like to just summarize briefly. So essentially, the capacity is lesser for a single reinforced section. So when we add reinforcement on the compression side, it enhances the moment and the moment capacity of the flexural members. Then the load which is being initially resisted by concrete in a singly reinforced section, that is going to be distributed between the concrete and steel in case of a doubly reinforced section. Yes, we can reduce the effect of creep on concrete in the compression zone. Then we can reduce the stresses within concrete. Then experimentally we are able to find out that when a beam is subjected to sustained loading, the deflections for the doubly reinforced sections is substantially lower when compared to the singly reinforced section. And whenever we are developing a reinforcing cage, so these compressive bars acts as hanger bars, and they help in keeping the lateral ties or the reinforcing or the transverse reinforcement in place. So these are some of the reasons for providing the compression reinforcement. So again, it helps in reducing the depth of neutral axis, which in turn enhances the curvature of the beam cross section, which in turn increases the ductility of the beam. Okay, and it helps in the fabrication, uses compression bars can the reinforcing steel in the compression region can be used as corner bars in order to hold and anchor the stirrups. Then we looked into the concept of effective reinforcement ratio and how it helps us in the determining the moment curvature relation for a doubly reinforced beam. Okay, and this is the slide where we expressed how we balance the forces that are developed on a doubly reinforced beam. So if we consider the same loading condition, when we consider a distributed loading on the beam along with a representative point load, so we have the bending moment diagram, and we need to develop we need to consider these forces in order to attain the equilibrium. So we have we consider the axial force, then we have the resultant compressive force that is developed in concrete, then we have the compressive force developed in the reinforcing steel, then we have the tensile force that is developed in the reinforcing steel. So if we equate this axial force equal to 0, then we need to balance only these three forces, as you can see. So the compressive forces within concrete and steel are acting in the left direction, and we have the tensile force within the reinforcing steel acting in the right direction. So in order to attain the equilibrium, we need to balance the compressive forces with the tensile forces, that is Cc plus Cs is equal to T. Okay, we are going to discuss more about these when we take up the numerical problems. So we essentially looked at certain numericals, and the procedure here also remains the same as we saw in the flow chart in the previous slide, previous part of the module. We essentially determine the value of we take a value of epsilon c, that is the strain within concrete, then we assume depth of the neutral axis, then we see then we determine the value of tensile force in the tension steel, then we determine the compressive force in the compression steel, then we determine the resultant compressive force developed in the within the concrete in the compressive region, then we try to balance it out, then we are going to determine the moment of resistance by multiplying the forces with the corresponding lever arm. Okay, so here are some of the plots that we developed from the analysis, and then we also looked at how we can develop the relation between the moment curvature and the load deflection plots for a beam. So this by integrating this particular relation for the curvature, we have 1 by r, that is equal to the curvature is equal to m by ei. So essentially by the process of integrating this particular equation 2 times and applying the boundary condition, we can obtain the relationship between the curvature within a beam and the corresponding deflection. So there are some problems in the assignment, so I encourage you all to try that, and if you are not able to obtain, we are always there to resolve the issues. So with that I hope we can start with the interaction session. Okay, yes. Yes, so we'll start with the first question. So question number 1 is before we proceed, if there are any questions, kindly feel free to ask, or we can straight away start with the question number 1. So question number 1 pertains to a singly reinforced beam without any actual compressive load. So I have taken this example so that we can evaluate what will be the influence of compressive force on a beam. So I request you all to take 3 to 4 minutes and let me know what would be the answer. So I will just repeat the data pertaining to this numerical. So we have a rectangular reinforced concrete beam which is having a width of 250 mm and overall depth of 450 mm. Concrete has a mean cylinder strength of 30 MPa, that is F prime C, and the beam is singly reinforced on the tension side with 4 HYSD bars of 20 mm diameter with an effective cover of 50 mm. So the question is to determine the ultimate moment capacity and curvature of the beam and assume Fy of the HYSD bars as 500 MPa.
Answer D.
Okay, thank you for the response. So for the other participants, I request you all to take 2 to 3 minutes. This problem we had solved in the previous weeks of live interaction session also. So it would be a good starting point before we can start with the concepts of effect of axial compression and compression reinforcement on the moment curvature behavior of a beam. Yes, would any of the participants would like to give the answer? If not, we can proceed with the solution. Okay, I think we can proceed. Yes, so as the participant rightly said, the correct answer is option D. So we are going to just refresh how we are going to solve this problem for those who could not join us last week. Okay, so so we have this singly reinforced beam right? Okay, so let me draw the strain profile for this particular so for this particular beam, what we need to find out is the moment of resistance, or the exact term is the ultimate moment capacity, right? So this would be the strain distribution along the depth of the cross section. We have epsilon c here, and this would be the depth of neutral axis, which we need to assume, right? So yes, to determine the ultimate moment capacity, we need to assume the value of epsilon c as 0.0035. So now we need to assume a value of x. So x value is basically an iterative process, as I was mentioning in the previous class also. So let us take the help of the Excel sheet in order to determine what should be the x value. Okay, so before proceeding to the x value, like I would like to first find out the value of alpha 1 and beta 1, which are used to determine the value of the coefficients for the compressive stress block. So we have the value of beta 1 is equal to so yes, beta 1 is equal to 4 minus epsilon c by epsilon prime c divided by 6 minus 2 times epsilon c by epsilon prime c. So if you plug the value of epsilon c as 0.0035 and then we plug the value of epsilon prime c, that is the strain corresponding to the peak stress, as 0.002, then we obtain a value of beta 1 is equal to 0.90. Okay, we are going to check these value in the Excel program also. Then we have to determine the value of alpha 1. Alpha 1 is given by 1 over beta 1, okay, into epsilon c by epsilon prime c minus 1 by 3 into epsilon c by epsilon prime c whole square. And when we again plug the value of epsilon c as 0.0035 and epsilon prime c as 0.002 and beta 1 as 0.90, we have the value of alpha 1 is equal to 0.8102. Okay, now in order to obtain the value of m and phi, we need to balance the compressive force with the tensile force. So let me do that next. Okay, so since it is a singly reinforced cross section, we need to simply equate the compressive force within concrete with the tensile force in the reinforcing steel. So compressive force is given by alpha 1 into f prime c into beta 1 into x into b. So b is the width of the beam. is equal to Ts is nothing but Fs into As. Okay, so how do you get the value of these? So let me first go to the Excel sheet and determine the value of x for you. Okay, so I think, yeah, we can go here, and I hope my screen is visible and the numbers are visible. Okay, so we have the width of the beam as 250 mm, overall depth is 450, and the effective depth turns out to be 400, and AST I have calculated and put the value here. Here's the percentage of steel. F prime C is 30 MPa. Okay, moving on. So essentially, let me put this value as 0 because we are not considering the effect of actual compression for this particular problem. Okay, so this is the value of epsilon C. So we need to balance out the value of the compressive force along with the tensile force. Okay, so for a depth of neutral axis of 338, we are getting a value of Cc as 1800 and Ts as 161. So the value of Cc is way higher. We need to reduce the value of x. Let's try 300. Still the Cc is very high. Let us reduce it to 50. Okay, still it is, the Cc is significantly high. Let's try 200. Still high. Let us try 180. Okay, but we are still high, but we are getting closer. Let me try 150. Still it is high. Let me reduce the value of x further. Let us try 130. Okay, still it is, Cc is higher. Let me try value of 110. So now we see that the value of Ts has surpassed the value of Cc. So we need to increase the value of x so that the value of compressive force within concrete is higher. So for a value of 114.9, we can see that the value of Cc and Ts are somewhat similar. Okay, 628.32 and 628.36. So we will consider a value of 114.9. Okay, let me go back to the problem once again. So let me write here as 114.9 mm. Right, so yes, now let us find out the value of tensile force. So in order to obtain this tensile force, let me call it as epsilon steel tension, right? So we have epsilon c by x is equal to epsilon st divided by d minus x. So when we plug let me substitute the values and see what answer we get. Epsilon c is 0.0035 divided by 114.9 is equal to epsilon st, we have to find out, divided by d is 400 minus 114.9. So can anybody tell me what would be the value of epsilon st?
And 0087.
Okay, just a minute. Okay, you're telling, okay, 0.0087, right? Yes, I'm going to yeah, consider 868 for better accuracy. Yes, so correspondingly Fs would be epsilon uh, sorry epsilon st into Es. So when we multiply this strain with 2 into 10 to the power 5, we get a value of 1736, which is higher than the yield value. So we consider the limiting value, which is 500 MPa. Right, so I think even in that Excel sheet also, I think it is trying to point out that only, because the yield value of strain is 0.0025. So this particular strain is much higher when compared to, it is almost 4 times when compared to this value. So it has yielded, so we need to consider a value of sigma t, or the FST, as 500 MPa. So yeah, let us go ahead with the calculations. So we have tensile force TS is equal to 500 into area of steel would be 1256.64. So what would this value be? Can anybody?
620.
Yes, so it is, as we saw, it was 628.3, I guess. Yes, and then we have the value of CC. CC is alpha 1 into F prime C. Let me just straight away substitute the values so that we can save on time. Yes, so CC, yeah, CC is equal to alpha 1 is 0.8102 into F prime C is 30 into beta 1. Beta 1 is 0.9 into X is 114.9 into 250, which gives us a value of 628.3. The participants can just verify with this value, right? Okay, so since we have balanced it out, we need to determine the value of the moment of resistance and the curvature. Pardon me, I need to make use of the space, so I'm going to start writing at this point here. So the moment value is let us consider ts into, so this would be d minus beta 1 into x divided by 2. Okay, so what would be the value of moment? Can anybody please tell?
219.06.
Yes. Okay, so the participant is telling that it is 219.06. Yes, and as per my calculation, there was a slight variation. I got 218.85, and phi value is nothing but epsilon c by x. So can anybody tell in terms of 10 to the power minus 6?
30.5.
Yeah, thank you for the response. So yes, yeah, 30.5. So if you go back and look at the answer, So yes, the answer is 218, and the moment of resistance is 218, and the curvature value is 30.5 into 10 to the power minus 6 per millimeter. So this was the starting point where we solved a numerical based on the moment curvature relation of the ultimate moment capacity of a singly reinforced cross section, right? So moving forward, we are going to evaluate what would be the effect of compressive force on the moment curvature relation. So before going to that, there is a question again on the singly reinforced cross section. I would like to just request you to solve the problem and let me know the answer. Okay. So we are considering the same dimensions for the beam. However, for the reinforcement, if we replace it by 4 bars of 20 mm diameter with 5 bars of 25 mm diameter, which type of failure is expected under the bending test? Okay, so for this problem, we don't need Excel program. It's not an iterative process. I request you all to take 3 to 4 minutes and come up with the answer. So before we can start the solution, can anybody tell what would be how you would approach this particular problem?
Reinforcement is increased, it is tension control failure.
I'm sorry, can you repeat, please?
Reinforcement is increased and it is tension control failure.
Okay, but this is a numerical example, so it can be compression controlled also, because when you increase the steel, so it can go into the previous example, it was an under info section, because the percentage of reinforcement was it was 1.1%. so we have not evaluated whether it is under enforced or not, but based on my calculation it was an under enforced section. But when we increase the amount of steel, it can be a balance section or it can be an over enforced section also. So when it's a balance section, it will be, when it's a balance section or a over enforced section, it can be a compression control failure also. Okay. Yeah, so please. Yeah, so please. Okay, so please go ahead and yeah, solve the problem and you can let me know the answer. So I think we can take one more minute and after that we can look at the solution. Okay, so any of the participants, do you have the answer?
I think
The
it
transition
is
control.
mixed failure.
Okay, okay, one of them is telling D, and what about the other participant? What do you think is the answer, sir?
Actually, stainless steel came 0.0062.
Okay, okay, so what do you think would be the answer?
Tension controls.
Attention control. Okay, okay, so I will go ahead and solve the problem. So the answer is option C. So you can just compare how I have solved, what was my approach to this particular problem, and check just your procedure also. So the way I approach this problem is that we have basically when we provide the reinforcement, depending on the area of steel that is being provided, right? Okay, let me switch the ink. Okay, so we have three types of sections. We have the first, we have the under reinforced, or we have the balance section, or we have the over reinforced. Okay, so under reinforced section, it is essentially tension control failure, while both the balance section and the over reinforced section, they are compression control failure. So while under reinforced section, we want to design the beam as under reinforced because it undergoes significant deformation and it gives us adequate warning before failure. However, for a balance section and an over reinforced section, a beam fails suddenly under flexural loading. So we want to avoid these two kinds of the beam design. So we have to look what is the definition of a balance section. So if we look at again the development of the strain profile along the depth of the cross section, so balance section is one which is defined as one where the crushing strain within concrete is attained at the same time at which the yielding of reinforcing steel happens. So what is the crushing strain of concrete? Epsilon C is 0.0035, and what is the yielding strain of steel? That is epsilon S is 0.0025. Okay, so if we have the value of epsilon C and epsilon S, we have the value of D, that is the effective depth. Effective depth is 400 mm. We can easily find out what is the value of the neutral axis depth. Okay, that is epsilon C by x is equal to epsilon S divided by D minus x by similar triangles. Okay, by solving these equations, this expression, by substituting the value of epsilon C as 0.0035 and epsilon S as 0.0025 and D as 400, I got a value of x is equal to 233.3 millimeter. Okay, then corresponding to this, we find out the value of CC, and we find out the value of TS. I mean, we need to balance these two forces. So let me take another. Yeah, so we have CC is equal to alpha 1 into F prime C into beta 1 into X into B is equal to Fs into AST. Okay, so we have all the values. We need to find out the value of alpha 1. So alpha 1, it is a function of epsilon C and epsilon prime C. Okay, so again based on my calculations, I got a value of 0.8102. it's also a function of beta 1. Okay, so and then we have the value of beta 1, which is a function of epsilon c and epsilon prime c. So this I got a value of 0.9. So the participants can kindly confirm this later on by substituting the value, the equations for alpha 1 and beta 1. So let me substitute these values. 0.8102 into f prime c is 30, into beta 1 is 0.9, into x is 233.33 into 250 is equal to, excuse me, fs we are considering corresponding to the yielding, the value of stress would be 500, okay, into AST. So this AST corresponds to a balanced section. Okay, so this AST balanced, we obtain the value as 2552.09 mm square. So what we can deduce from this from this value of AST is that any value which is less than this one, it is an underinfo section. Okay, and any value which is greater than this becomes an overinfo section. Okay, so when we find out the AST corresponding to 5 of 25 mm diameter, what is the value of AST? Can anybody tell?
2455.
Yes, thanks for your answer. So the value of AST would be 2455 mm square. So since this particular value is less than AST balanced, we can conclude that it is an underinfo section. Okay, hence it is tension controlled. So I hope the participants were able to follow. If there is any question, we can proceed, or else we can if there is any doubt, we can answer that, or we can proceed with the session. So it is since it is underenforced, it is a tension controlled failure mode. So underenforced is tension controlled. On the other hand, if it is a balanced section or an overinforced, it becomes a compression control. Okay, so if there are no questions, we can proceed with the next question. So question number 3 is, when a beam under flexure is subjected to axial compression, which of these equations represent the force balance equation?
Option A.
Okay, thank you for the response. Any other participant would like to confirm this response?
Yes.
Okay. So as the participant mentioned, it is a simple force balance question. So the correct answer is option A. So when we are dealing with the additional compressive force that is acting on the beam, we need to balance these forces. So as I was already mentioning, the resultant compressive force acting on concrete, that acts in the left direction. On the other hand, the actual compression and the tensile force that is developed in the reinforcing steel, these two forces act along the right direction. So when we balance these two, we get Ts plus P is equal to Cc. So yeah, option A is the correct answer. So we have the numerical here. So we are going to see the effect of compressive force on the moment curvature behavior of a beam. So I'll read out the data of this particular problem. So we have a beam that is similar to the question 1. It is having a width of 250 mm and overall depth of 450 mm, and the cylinder has a mean compressive strength of 30 MPa, and the beam is reinforced with 4 bars of 20 mm dia, and the yield stress is 500 MPa. The reinforcement is provided on the tension side with an effective cover of 50 mm, and the major difference is that the beam is subjected to an axial compressive force of 10% of the axial capacity, considering only the contribution of concrete. Okay, so this is the axial compressive force, 0.1 F prime C into Ag. So we need to determine the moment of resistance and the curvature corresponding to a concrete strain of 0.0005. Okay, we need Excel program in order to solve this problem. I hope the participants have prepared the Excel program. I will request you to solve the problem. We can take 2 minutes, and after that we are going to look at the solution. Okay, please take 2 minutes for this problem.
Answer C.
Okay, thank you for the response. We can take another 1 minute. After that we can start with the solution.
Option C.
Yeah, thank you for the response. Okay, so as the participants have answered without any further delay, yeah, the answer is absolutely right. It's option C, and I'm glad that I hope that both of the participants have developed their Excel sheets in order to solve this problem. So for the benefit of other participants, I am going to solve the problem now. Okay, so let us consider the cross section. So it is being subjected to an axial force of P. Okay. So the value of P would be 0.1 F prime C into AG, right? So 0.1 into 30 into AG, that would be 250 by 400. So what would be the value of P? Can anybody answer?
$337.5.
Okay. Yes, so the value is 337.5 kilonewton. So this is the force that is acting, actual compressive force. Let us draw the stress distribution along the depth of the cross section, right? So yeah, so we have epsilon C, right? So we need to find out for a value corresponding to 0.0005. Then we have epsilon S T. Okay, so this would be the depth of the neutral axis. Okay, so let us go and check as to what would be the x for which we are going to get the force balance between the compressive and the tensile force and the actual compression. So the value is same, value of B is same, D is same, and for this let us plug a value of 0.1, for which we got the value of 337.5 kilonewton. Value of epsilon C is 0.0005, right? And we have compressive force as 197, and the value of tensile force is 311, and P is 337.5. The summation of actual compressive force and the tensile force, that is 649. So it is very high when compared to the compressive force. We need to increase the value of x. So let us progressively increase the value of x, and for 120 I will not waste any time because the participants have got the answer. So I got the force equilibrium for a value of 243.4. Yeah, I hope for the participants also, like you also got a value of x as 243.4.
Yes, sir.
Yeah, thanks for confirming. So as you can see, we are able to balance these two forces, these three forces rather. Cc is equal to 418.3 kilonewton, and similarly P plus Ts is 418.35 kilonewton. So we will go ahead with the calculation. I am going to show the calculation for this particular case, and for the remaining strain values we are going to determine solely on the basis of the Excel program. So allow me to perform the calculations for this particular for this particular problem. So we got the value of x as
243.4.
yeah, thank you, 243.4 millimeter. Okay, right. So we have epsilon c by x is equal to epsilon st divided by d minus x. So when we substitute the values, 0.0005 by 243.4 is equal to epsilon st we need to find out divided by 400 minus 243.4. Pardon me for my poor handwriting. Epsilon st, what would be the value of epsilon st? Can anybody confirm?
00032.
Okay, okay. So let us look. Yeah, as we can see in the Excel program, it is 0.000 0.00032, and correspondingly, what would be the value of FST? Multiply it by the value of Young's modulus.
64.33.
Yeah, thank you for confirming. So it is, yeah, 64.34. Let us round off the second decimal point. 64.34, right? 64.34 MPa. And please note that this particular strain value is less than the yield strain. Okay, so we have the tensile force Ts is equal to Fs multiplied by As, that is 64.34 multiplied by 1256.64, and what would be this value Ts?
418.3.
Just the value of Ts, please. So Ts would be, yeah, 80.85.
हम थोड़ा लेसन के जाएं.
Yeah, 80.85. I think you are referred to P plus Ts, but that is why, that is fine. We'll come to that step later on. And let us find out the value of Cc. Cc is equal to, yeah, alpha 1 f prime c beta 1 into x into b. So that would be alpha 1 and beta 1, for values of 0.0005. I got alpha 1 as 0.3361, and 30 into beta 1 would be 0.6818, and the value of x as we obtained is 243.4 multiplied by 250. Okay, we obtain the value of Cc as 418.34 kilonewton. So we need to balance the forces now. That is, let me change the ink, right? In order to satisfy equilibrium, Cc is equal to P plus Ts, right? So we see that 418.3 is equal to 337.5 plus 80.85. So now let me for the final step, moment of resistance corresponding to a concrete strain of 0.0005 in the extreme compression fiber, M is equal to, we are considering the moment about the about this centroidal axis, about which this force P is acting. So we can, if this is the cross section, we can consider that this is the point through which the force P is acting. So M is given by M is given by Ts into d minus capital D by 2 plus Cc into capital D is the overall depth, minus, I'll try to accommodate it here only, beta 1 into x divided by 2. So when we plug the values, we have the value of Ts, we have the value of effective depth, then the overall depth, we have the value of compressive force 418, we have overall depth beta 1 into neutral axis depth, we have all the values. When we plug all these values, we get a value of
73.56.
yes, yeah, 73.56 kilonewton meter. Yeah, and we have the value of curvature is epsilon c divided by x, that is
2.05.
yeah, thank you, 2.05 into 10 to the power minus 6 mm to the power minus 1. Okay, so yeah, which is why option C is the right answer. Yeah, so this is for the benefit of the participants who are not able to solve, or yeah, they can check this after watching the recording of this video. So we ultimately obtain these values of m and phi corresponding to epsilon c as epsilon c of 0.0005. Now we move on. So for the beam given in question 4, what would be the corresponding moment of resistance and curvature for a strain of 0.001? Okay, we have essentially doubled the value of strain in concrete from the previous example. So kindly take 1 or 2 minutes and tell me the value of m and phi.
Option B.
B for Bangalore.
Bangalore.
Yeah, thanks for the response. Anybody else would like to confirm?
B.
Okay, thank you. Thanks for the response. Okay, so I think we can go ahead with the correct answer. So the correct answer is option B. I presume that the participants, both of you have developed your own Excel sheet.
Yes, sir.
Yeah. Since it is an iterative process, it is practically impossible, to do it using pen and paper. So once you have all this data, yeah, you can. So since it is a course on advanced reinforced concrete design, once we have this these spreadsheets, we can easily solve, and we can actually plot the moment curvature plots also. And yeah, I was not initially sharing these spreadsheet uh, because our assignments are based on these problems. So once the assignment solutions are out, I'll be happy to share with the group, for the benefit of others who are not able to do it. But I think since your assignment marks is considered for the final grading, and it will affect your final performance, so I recommend all of you to develop your own Excel sheets. And if not, later you can always refer to the sheets that I have developed and compare if there is any elements which which you might have missed. You can incorporate that also. So
Sir, actually, sir, for this problem solving section, we need that detailed solutions.
yeah, sure.
And that one,
Yeah,
previous one,
yes.
we got answer but unable to check, sir, where it's missed.
Okay, sir. Actually, we will tell Professor Surya Prakash sir also, and we will work on it, and we will make sure that you will get the solutions, the detailed solution also. Thanks for
Actually, for
yeah.
dynamics of features, we are getting every assignment. We are getting detailed solution.
Okay. Yes, sir. Yeah. So we have all solved the solution. So basically, yeah, I will request the the TAs who are responsible for those particular assignments to develop the solution, and we can share it with the participants as soon as possible. Yeah, so we will go ahead. Let us solve this problem for a strain in concrete corresponding to 0.001. So the value of CC is high. Let us reduce it. Let us try 220. Yeah, actually, since the participants have got the correct answer, I think we can directly go ahead with the yeah, for a value of 193.7. Yeah, we were able to balance these two forces, CC and P plus TS, and the corresponding value of moment is 142 kilonewton meter and 5.16 into 10 to the minus 6 per millimeter. 142 and 5.16. Yeah, 142 and yeah, 5.16. Option B is the correct answer. Okay. Yeah, thanks for the response. We can proceed to the next question. Now, what would be the value of M and phi corresponding to concrete strain of 0.0015?
Answer is D, sir.
Okay, thank you for the response. Anybody else would like to confirm? Okay, so I think we can go ahead with the answer, and the correct answer is option D, absolutely right. So we can go to the Excel sheet and just verify that. Let us plug a value of 0.0015, and for this I got for a value of 184.4. I was able to balance the forces 778, yes, 778 and 778, and the corresponding moment m is 200.37 and phi is 8.14, 208.14. so option D. Yeah, option D is the right answer. Yeah, thanks for the answer. Moving forward, what would be the m and phi for 0.002? Kindly take 1 minute.
Yes.
Okay, option A. Okay, anybody else would like to confirm? Okay, I think we can proceed with the solution. Yeah, option A is right. We can verify that with the Excel sheet. So we have a strain in concrete as 0.002, and for this particular strain in concrete I got for x value of 184.7, okay, so I was able to attain so I was able to balance these forces, that is 923 and 923, and correspondingly the value of m is 246.4 and 10.82 into 10 to the power minus 6, 246 and 10.82. Yeah, so 246 and 10.83. Yeah, that is the right answer. So I request to all the participants to develop similar Excel sheet. So if there is any problem, you can rectify the mistake, and basically how I calibrate this is based on the examples worked out by sir Surya Prakash sir in the lecture. So whatever examples I have, examples that is solved in the class, I try to calibrate my Excel program with the help of those examples. After that I develop problems and I try to solve using this, so you can develop similar in a similar fashion. Okay, moving on. So what would be the moment and curvature corresponding to concrete strain of 0.0035? Okay, kindly take 30 seconds to 1 minute to solve this problem.
Option C.
Okay, thank you for the response. Okay, anybody else would like to confirm? Okay.
Yes, sir. C.
Okay. Thank you. The correct answer is, yeah, absolutely right. It is option C is the correct answer. Thank you for the response to the participants. Let's go back to the Excel sheet and yeah, 0.0035. We will consider the peak value of strain as 0.0035 and corresponding to neutral axis depth of 176.6. I was able to balance these two forces approximately 756.8 and 756.8, and the corresponding moment value is 250, 250.5 and 19.82. 250.5 and 19.82. Option C is the right answer. Now let us look at the next question. So we have to plot the moment curvature graph for the beam given in question 4 based on the results that we obtained from question 4 to question 8. So in question 4 to question 8, what we did was we basically varied the value of compressive strain in the extreme compressive fiber, then correspondingly we got the values of moment and curvature. So what do we get when we plot these values? Okay, so we got this, the plot is basically corresponding to 10% of the actual capacity. We got this plot which is in blue color, and this is corresponding to a beam where there is no actual compressive force that is acting. So we see that when there is when we introduce a value of when we introduce a compressive force corresponding to 10% of the actual capacity, so there is a slight increase in the moment capacity, but there is a reduction in the curvature. Okay, so what we are going to do is we are going to increase this actual force. So as we can see, up to 20% we take the beam action, and beyond 20% we take the beam column action. Then we are going to see how the moment curvature varies for values of 20%, 30%, 40% and 50% and so on. Okay, so yes, we can go on to the next question. Okay, kindly solve this problem. Again, the beam is same as in question 4. So what would be the moment of resistance and curvature corresponding to a concrete strain of 0.0035 for a force of 20% of the actual compressive capacity of the column? Kindly take 1 minute for this. Yes, anybody got the answer? If you are able to factor in the three forces properly in the Excel sheet.
Answer B.
Okay, thank you for the response. We will wait for another 30 seconds if the other participants would like to contribute. Okay, I think we can look at the answer now. Yes, answer B is absolutely right. I initially had thought of solving the problem, but I think we can since we have a few more questions lined up for this session, we can straightly solve it in the Excel spreadsheet. Okay. So what we are doing is from 10% we are increasing it to 20%. Let's take it as make it 0.2, and the corresponding actual force, actual compressive force is 675 kilonewton, and the value of epsilon c is 0.0035. Now for x value of 235.62, let's see what happens. Yeah, I was able to balance the forces 1288.5 kilonewton and 1288.7 kilonewton. We can make allowances for small imbalance between the forces. So the corresponding value is 260.7 and 14.85 for M and 5. Yes, so 260.7 and 14.85. Thank you for the response. So now let us see what would be the next question. What would be the moment of resistance and the ultimate curvature corresponding to a compressive force of 30% of the actual compressive capacity? Okay, kindly take 1 minute and let me know the answers.
Option E.
Yeah, thank you for the response. We will wait for another 30 seconds, then we can go ahead with the correct answer. Okay, so option A is absolutely right. So let us go to the Excel sheet and see how we can solve the problem. So here I am entering a value of 0.3 as the percentage actual capacity of the column. So the corresponding actual compression would be 1012.5 kilonewton, and epsilon c is 0.0035. and for a value of 266.1, let's see what happens. Yes, I was able to balance the two forces, or rather the three forces. CC is 1455.2 kilonewton and P plus TS is 1455.13 kilonewton, and the corresponding moment and curvature would be 230.63 and 13.15. Yes, 230.63 and 13.15. Option E is the right answer. Now we'll go to the next question. Now what would be the value of M and phi corresponding to a compressive force of 40% of the axial capacity? Okay, kindly take 30 seconds.
Option A.
Okay, thank you for the response. Yeah, without any further delay, so we'll give the answer. So option is right. So let's go back to the Excel sheet, and yeah, we will change the value to 40% of the actual capacity, and the compressive force is 1350 kilonewton, and for a strain value of 0.0035, and let's see what happens when we substitute the value of x as 300.3 kilonewton. I'm sorry, 300.3 millimeter. Yes, we are able to balance the three forces, 1642 kilonewton and 1642 kilonewton, and the corresponding moment and curvature values are 198.69 and 11.66. So yeah, 198.69 and 11.66. So option A is absolutely right. So moving to the next problem. So lastly, what happens when the compressive force is 50% of the actual capacity, considering only the concrete contribution?
Option C.
Yeah. Thank you for the response. Yeah, since the previous answers are correct, yeah, even this also. Let's not waste any time, and option C is indeed the right answer. Thank you for the response. So yeah, let us go to the Excel sheet and enter a value of 0.5. The corresponding compressive force is, actual compressive force is 1687.5, and epsilon c is 0.0035, and for a value for x value of 338.1 millimeter, I was able to balance the three forces, 1848 kilonewton and 1848 kilonewton. Okay, and the corresponding m and phi values are 162.9 kilonewton meter and 10.35 into 10 to the power minus 6 per millimeter. So 162.89, 10.35. Yeah, 162.89 and 10.35 points. Option C is absolutely right. So let us see what would be the moment curvature plots for the beam given in question 4, corresponding to different levels of axial forces. So this is how it varies. Now let us dwell on this graph and understand what it is trying to tell us about the flexural behavior of beams corresponding to different levels of axial load. So this orange So this orange plot corresponds to the moment curvature plot where no axial force is acting, and then we have the blue plot which corresponds to 10% of the axial load. Then we have this light blue turquoise color corresponding to 30% of the axial load, and then this purple corresponds to 40% and green corresponds to the 50%. So here we can see that the actual force up to 30% is quite beneficial in increasing the moment capacity. However, it has reduced the curvature capacity. As you can see, from a value of 30 into 10 to the power minus 6, it has reduced to 20 into 10 to the power minus 6. And beyond actual compression of 30%, that is for 40% and 50%, we are able to see a degradation of both the moment capacity as well as the curvature capacity. So it is not only reducing the strength value, it is reducing the ductility also. Okay, so we need to keep this in mind, that up to a certain value, let's say up to 20% of the actual capacity, considering the contribution of concrete, the actual force is beneficial to enhance the moment capacity of the beam, but the curvature it suffers to a certain extent. But beyond 30%, the actual force is detrimental to both the moment capacity as well as the curvature capacity of the beam. Okay, so we will take up a theoretical question, conceptual question based on this.
Excuse me, sir.
Yeah, please go.
Yeah, in question number 14.
Yes.
Yeah, regarding this graph, I have a question.
Yeah.
Is this axial force related somewhere to the pre-tensioning of the beam, or is it something? What does this actually? What does this axial force in the beam refers to? Can you please
So
explain?
yeah, that is a very good question. So as you pointed out, this corresponds to we are considering the concept of beam column. So when you consider a column, so let me take this. So if we consider a column, so a column, as we were discussing in one of the earlier lectures, it is not only subjected to this actual force, along with that it is subjected to these shear force and moment also. Okay, so we are trying to study the behavior in addition to the flexure. This moment and shear, it is a resultant of some lateral force that is acting, let us call it as F. So we are trying to essentially evaluate how the behavior changes when we are introducing this value of P. So this pre-stressing, it is a different concept, but I will just look into it and let you know, because presently we are dealing with only with the reinforced concrete structures, but it is a very interesting question. I will dwell into that, but as far as my understanding goes, I think we are essentially looking into this only, like we are trying to see this beam column element, which is subjected to not only the flexural and shear forces. We are also trying to understand the implication of introducing this actual compression, and yeah, we are trying to evaluate this, but I will get back to you regarding the pre-stressing for the
Okay, thank you so much, sir.
yeah, thanks for the question. And yeah, so we have a conceptual question. Yeah, just try to which of these statements actually describes the influence of limited axial force, let us say 20% of the axial capacity considering concrete, on the moment curvature behavior of a singly reinforced beam.
Option C.
Yeah, option C is absolutely right. So as we discussed in the previous slide, up to a value of 20%, it is beneficial to it is enhances the moment capacity, but curvature, it is detrimental, it decreases the curvature capacity of the beam. So option C is the right answer. So we can go to the next question. So when we consider a doubly reinforced beam, what is the expression for effective reinforcement ratio? Okay, so if rho is the reinforcement ratio on the tension side, rho prime is the reinforcement ratio on the compression side, how to express effective reinforcement ratio?
So B,
Option D.
Okay, a B for Bangalore or D for Delhi?
Bombay.
Delhi.
Yeah, yeah, thanks for the response, and it is quite straightforward, absolutely right. So yeah, the effective reinforcement ratio is given by rho minus rho prime. Okay, so as we have it has become a norm actually since the last three classes. We have been since we started around 7:10, we will be extending by another 10 minutes. I hope it is okay for the participants. I think I have another 4 questions lined up for you.
Okay, sir.
Yeah, yeah, thanks for the confirmation. So now we are diving into the realm of the doubly reinforced members. Yeah, so kindly take a few minutes, 2 to 3 minutes. So what we have here is a doubly reinforced beam. So the cross section dimensions are 250 mm width and 450 mm overall depth, and the concrete has a mean cylinder strength of 30 MPa, and the tension reinforcement remains the same. It consists of 4 rebars of 20 mm diameter, and we are introducing reinforcing steel on the compression side with an area of 600 mm square, which is having an effective cover of 50 mm both on the compression steel as well as the tension steel. What would be the moment of resistance and curvature corresponding to a concrete strain of 0.0005, and assume uh, the yield strength of reinforcing steel as 500 MPa. So if you have the Excel sheet ready, kindly take 1 or 2 minutes and kindly give me the answer. Okay, anybody was able to obtain the answer?
Yeah.
Okay, okay, thank you for the response. Yeah, thank you for the response. Anybody else? So since we are overshooting, the time, I will go ahead and show the solution. Yeah, option A is absolutely right. Okay, let me solve. Since we are dealing with the W info section for the first time in today's session. Yeah, so we are looking at the strain distribution along the depth of the cross section. Okay, so we are interested with the strain values at 3 points, epsilon c, and this is corresponding to compression C, epsilon SC, and here we have epsilon ST, and we need to find out for point 0005, right? So yeah, based on similar triangles, epsilon c by x is equal to epsilon st divided by d minus x. So we need to go back to the spreadsheet. So I already have it ready for, yeah, so 250, 450, and let me change the value of AST is 1256.64 mm square, and AC we have 600 mm square, right? Yeah, so D prime is 50 MPa and epsilon c, yeah, the rest of the data is fine, 0.0005, and for a value of x is equal to 130.1, let's see what happens. Yeah, so we are able to balance approximately the value of TS on the one hand and CC plus CS on the other hand, that is force in the tension steel and effective force in the compression block of concrete and the compression steel. Okay, it is approximately 260, and yeah, for this we have a value of 130.6 by taking a value of x is equal to 130.1 millimeter. Okay, okay, we get value of epsilon st is equal to how much? I got 1.001037, right? So we have fst is equal to epsilon st into es. So let me straight away jump into the value of ts, that is tensile force in the steel is given by, oh I'm sorry, tensile force in the steel is given by 260.7. Yeah, we have 260 point, sorry, 0.7 kilonewton, right? So this is the value of ts that we have. Now let us look at the compressive forces in using a different color. Okay, so we have cc is equal to alpha 1 f prime c into beta 1 into x into b. Okay, so for a value of 0.0005 we have alpha 1 is equal to beta 1 is equal to, yeah, alpha 1 is 0.3361, and beta 1 is 0.6818. So when we plug the values, we get value of Cc as Cc is 223.61 kilonewton, 223.61 kilonewton. Okay, then we have the value of Cs. So before proceeding to Cs, we need to determine the value of epsilon Sc. So we have epsilon C by x is equal to epsilon Sc divided by x minus d prime. Okay, so d prime is the the effective cover for the compression steel. So substituting, we have the value of epsilon Sc as, where do we have epsilon Sc? Yeah, epsilon Sc is 0.00031. We have 0.00031, and correspondingly we have Cs is equal to epsilon Sc into Es into ASc. ASc is 600 mm square. By plugging the values, we get the value of Cs as, yes, 36.94 kilonewton, right? So we are able to balance these three forces, and let me take a different ink here, and we need to balance Cc plus Cs is equal to Ts. Okay, and for this particular case, the moment of resistance, we can take the moment of resistance about the tensile force, that is Cs into d minus d prime plus Cc into d minus beta 1 into x divided by 2, for which we get a value of, what was the answer? We get a value of 92.46 kilonewton meter, and pardon me, we get the value of phi is equal to epsilon c by x, that is 3.84 into 10 to the minus 6 per millimeter. Okay, yeah, so we have 92.46 and 3.84. Yeah, so option A is the right answer. Okay, so let us see what happens next. So what would be the moment of resistance for the same cross section corresponding to a concrete strain of 0.0035? Kindly take 30 seconds, and then we'll look at the answer and the solution.
Option C.
Okay, thank you for the response. Yeah, so we look at the answer. I'm sorry. Yeah, option C is absolutely right. So let us go and change the value of strain here, 0.0035, and when I plug value of x as 83.86, let's see what happens. We are able to balance the three forces. 628 here tensile force and the compressive forces are 628, and the corresponding moment is 225.5 and 41.74. Yeah, so option C is the right answer. So let us see how the moment curvature varies for a singly reinforced beam that we considered in the question number 1 and doubly reinforced beam that we considered in the last just solved example. So as we can see, this orange plot corresponds to the singly reinforced beam, and for a doubly reinforced beam we can see that the moment capacity is approximately the same, because the area of steel in the tension zone was quite low. It was under reinforced section. As we can see, it was just 1.12%, and the compressive steel has added just to the curvature capacity. Okay, so yeah, this was the outcome. Now we are going to take up another problem where we are going to enhance the area of steel significantly. Okay, from 1.12% we are going to enhance it to 4%. Then we are going to enhance the compression steel to 2%, okay, which is here. Then we are going to see what would be the influence on the moment curvature response. Okay, yeah, kindly use this data, take 1 minute and let me know the answer. So as I was explaining, the dimensions of the beam remains the same, but we are changing the area of tension steel from 1.12% to 4%, and then we are increasing the area of compression steel from 0.53% to 2%. So what would be the corresponding moment of resistance and curvature corresponding to a concrete strain of 0.0035 in the extreme compression zone, in the extreme compression fiber?
Option D.
Okay, thank you for the response. Okay, so we can take another 15 seconds. Okay, option D is absolutely right. So thanks for the response. So yeah, I think we can go to the Excel sheet and we can solve the problem. So what happens here is we are going to increase the AST to 4500, which is 4% of tension steel, and increase AAC to 2250, that increases to 2%. Then what happens for epsilon c is equal to 0.0035 when we plug the value of x as 205.7. okay, we are able to balance the tensile force and the compressive force, and the corresponding moment is 740 kilonewton meter, and the curvature is 17.02 into 10 to the power minus 6 per millimeter, radians per millimeter. Okay, yeah, so option D is absolutely right. And so what we are trying to do here is we are going to plot the moment curvature graph for the doubly reinforced beam given in question 20, and we will compare the moment curvature graph when the same beam is singly reinforced. Okay, when we retain the tension reinforcement but we will take away the 2% compression reinforcement, then we will see how the moment curvature plot is going to vary. Okay, so this is interesting, isn't it? Because in the previous example we provided only 1 1.12% of tension steel, and the moment capacity was comparable and the curvature was increased. But in this case we are going to provide a higher proportion of tension steel, and even we are going to increase the compression steel also, and the effective, let me write it down. We have rho is equal to 4% and rho prime is equal to 2%, and the effective reinforcement was rho minus rho prime is equal to 2%. Okay, so this is what happens when it is doubly reinforced, and when we have just steel on the tension side, when it is singly reinforced, we get this behavior. Okay, so here we not only see that when compared to a singly reinforced section, as we were seeing, why I chose this 4% is because as per IS 456, that is the Indian Code of Practice for Reinforced Concrete Structures, the maximum steel that can be provided in the tension zone is 4%. So if we just provide the tension the steel in the tension side, this is the value of moment and curvature that we obtain. But when we supplement this tension reinforcement with a compression steel of another 2% compression steel, so we can see how the value of moment and curvature, how it significantly is enhanced. So from 400 to close to 750, almost there is an increase of increase by close to 90%, I presume. So it is substantial increase in the moment capacity, and also the curvature also we are increasing from like 12 into 10 to the power minus 6 to almost 18. So there is almost 50% increase in the curvature capacity. So this goes to show the importance of providing compression reinforcement when we want to increase the moment capacity and the curvature capacity. So with that slide, we will come to a conclusion of today's live interaction session. So I thank you all for joining, and one last note before we end today's session is that I was very pleased that how you are able to participate in the live interaction session. I was very happy with how the participants came prepared with their own Excel sheet. So what I am trying to do is I refer to the lectures of Surya Prakash sir, and I try to prepare the assignment questions so that it helps you in solving the assignment questions. So apart from this, if you need any help or any general discussion with respect to the areas that we are covering weekly, so I'll be happy to address them. So I think yeah, on that note, if there is any feedback or suggestions from your side, I'm I'll be happy to answer that, or we can just end the session for tonight.
Thank you so much, sir. Thank you so much, NPTEL team and
Yeah,
professor. This is such a beautiful course. We are enjoying it.
yeah.
Thank you so much.
Yeah, thank you. It means a lot, because every week I'm devoting 1.5 to 2 days to prepare the presentation for this, and it really means a lot moving forward. And if you'd like to apart from the assignment questions, as one of our other participants, they were asking if there is any other standard text also. So if you want to practice problems from any other standard sources like Pillai and Menon, If you come across any problem, you can raise it in the discussion. I'll be happy to take it up in the live interaction session. And we have completed 50% of the lecture, the course so far, and I hope that we can successfully completing the remaining lectures and the live interaction session also. And yeah, thank you a lot. It means a lot that even if the participants are also coming prepared. So I hope that we can truly enjoy this learning, and make something out of this in our professional and academic practice. On that note,
Okay, sir.
yeah, on that note, if there are no other feedback, questions, comments, we can conclude the session. I thank you for your patience. I know you have been putting up with me, with these long classes. So yeah, thank you so much. Okay, good night to all of you.
Good night.